The reactions of monosaccharides is going to be the topic of this lesson. We'll cover ester formation, ether formation, glycoside formation, isomerization and epimerization. We'll spend a little bit of time talking about oxidation and reduction. And then finally, a couple classic syntheses reactions. One that lengthens the chain of a monosaccharide by one carbon, the Kiliani-Fischer synthesis, and then one that's going to reduce the carbon chain by one carbon, the Wohl degradation. So we'll start here with ester formation, and we learned it earlier in the chapter on carboxylic acids and derivatives that when you react an alcohol with an acid chloride or an acid anhydride, you can form an ester, and that's exactly what we're doing here. So earlier we'd seen something more, and we looked at this more usually from the perspective of the acid chloride in those contexts. So we can add any kind of alcohol here. So, and we're gonna do nucleophilic attack. We'll kick these electrons up, but they'll come right back down and kick off that chloride. So, and eventually it'll get deprotonated. So, and we will have formed an ester. So, and you can do this with the acid chloride. You can also do it with the acid anhydride. And the idea is that in either case, you've got a pretty decent leaving group that's going to get replaced by that alkoxy group to result in an ester. Well, in this case, one thing we want to distinguish here is that you could do this with any of the alcohols, but also this guy right here is not an alcohol. That's part of the hemiacetal. This carbon right here is the anomeric carbon. You'll see in a little while why I'm emphasizing that. So, but that one is reactive in this reaction as well. You can form an ester at every single one of these locations. And so every single of the hydroxy groups, as long as you had excess of the acid chloride or the acid anhydride with a little bit of base, in this case pyridine, so, and you'll find out that we've got esters in all of these locations. Now, one thing to note, we get a little bit lazy sometimes, and so sometimes we'll write this instead, like this group right here. We'll just write it as OAC, because this is an acetyl group. So be prepared to kind of see it both ways. And I drew it out because I figured that just be a little more helpful in this case, but be prepared, you might see it this way as well. It means the same thing. That's ester formation. Now, very similar to ester formation is going to be ether formation. And in this case, instead of an acid chloride or an acid anhydride, we're just going to have an alkyl halide in this case. So, and in this case, we're going to make it methyl halide. So great for SN2 backside attack. So in this case, that's exactly what we're going to do here. So we've got silver oxide, and silver oxide is basic, so it can lead to the deprotonation of this hydroxyl group right here, making it an even better nucleophile. So, and it's going to do backside attack, and ultimately that hydrogen, which has been deprotonated by the basic conditions, is going to be replaced by a methyl group in this case. And once again, I just want to point out that, again, we've got 4 alcohol groups, but again, this guy's technically not an alcohol. He's a hydroxyl group, but not an alcohol. He's part of that hemiacetal coming off the anomeric carbon here. And again, I want to emphasize that, again, whether it's the alcohols or the hydroxyl of the hemiacetal, they're all reacting to form ethers in this case. So now we want to take a look at glycoside formation. Glycoside formation is going to be a specific reaction only at the hemiacetal hydroxyl group, only at the anomeric carbon. And this is why I've been emphasizing where that anomeric carbon is on the previous reactions. With ester formation and ether formation, it didn't matter. All the hydroxyl groups were reactive. But here with glycoside formation, it is only that hydroxyl group on the anomeric carbon. And again, you can recognize it as the one that's bonded to 2 oxygens where one of them is an OH. So none of these other alcohols are bonded to a carbon that's bonded to 2 oxygens, just the anomeric one. And that's your hemiacetal, and it's the one that's reactive in this case. I want to take you back to something we learned in the ketone aldehyde chapter when you add multiple equivalents of alcohol with an acid catalyst to a ketone or aldehyde. So in this case, after you've added 1 equivalent, so this oxygen of the ketone here is going to become the hydroxyl group, and now you'll have added 1 equivalent of your alcohol, and this is your hemiacetal. It is halfway to an acetal, and hence the name. So, and then we'll go ahead and add a second equivalent here. So this OH is going to get protonated and leave as a leaving group and get replaced by yet that second equivalent. So, and that is your acetal. Okay, and again, you can recognize it here because you've got a carbon here that's bonded to 2 oxygen atoms, neither of which is an OH. They're both OR groups. That's your acetal. Now, when we did this back in the ketone aldehyde chapter, normally we considered adding 2 equivalents of exactly the same alcohol. Well, here we've already got a hemiacetal. This was formed from the cyclization of your monosaccharide. The first hydroxyl group that added was already part of that monosaccharide. The second one, though, is going to be from another source. And in this case, I'm adding, methanol. So in other cases, we'll find out that when we form like disaccharides and polysaccharides and stuff like this, it can actually come from a different monosaccharide as well in forming a glycosidic linkage. So, in this case, I'm going to choose methanol as my choice. And ultimately, this OH, just like it did here, this OH right here gets replaced with another OCH3. And this OH is getting replaced with an OCH3 along the formation. Again, you can recognize this is your hemiacetal because once again, you've got a carbon that's bonded to two oxygens, and neither one of them is an OH. That's an acetal, and we call that a glycoside. So when it's in the hemiacetal formation, that is not a glycoside. But once it's converted into an acetal, that is now a glycoside. All right, so now we want to talk about both epimerization and isomerization. So both these reactions can take place when you've got a monosaccharide in aqueous solution under basic conditions. So I want to remind you of keto-enol tautomerization here. So, and it doesn't have to be a ketone, it could be an aldehyde. So with this keto-enol tautomerization, notice you've got the enol here in this case. And so between your alpha carbon and then the carbonyl carbon, that's where the ene would normally be. So, and then what was the carbonyl before becomes the alcohol in that enol form. Well, in this case, again, here's your alpha carbon right here. So, and then your carbonyl carbon, and that's where we're going to have an ene. So in this tautomerization reaction, but notice it's not just a regular enol because both sides of the alkene part of it are attached to an OH. And so it's what we call an enediol in this case. And so we got a couple different options of what could happen here. So we could just go back. So go right back to what we had. So and go right back to the corresponding keto form, which in this case is an aldehyde. So the problem though is that when we do this, so in this enediol form, this carbon right here is no longer a chiral center. So it goes from being sp3 hybridized and chiral to being sp2 hybridized, trigonal, planar, and flat. Well, when it goes back, it has the option. It could open up either way. It could open to reform the original, so D-glucose, or it could give you the opposite configuration as well, so to give you D-mannose. And so in this case, that's the epimerization part. So the D-glucose you start with and the D-mannose that you might end up with some of at the end, so are differ in one chiral center. So they're a special type, again, of diastereomere we learned in the last lesson called epimers, and there's your epimerization reaction. Now the other option, so is that it's an enol with two different hydroxy groups here, one here and one here. And instead of when it goes back to forming a carbonyl group, instead of forming the aldehyde one, which is what we had in the first step, it could isomerize back to form the carbonyl here instead and give a ketone instead, a ketose in this case, D-fructose. So, and in that case, we wouldn't call it epimerization, so because they wouldn't even be stereoisomers, they're going to be constitutional isomers, and so we just call it isomerization here. And so, starting with D-glucose, you could end up getting the corresponding ketose one carbon away, and that's isomerization. Again, both these reactions occurring under basic conditions. We'll see that'll be important in a couple of the reactions we talk about a little bit later down the road. So now we want to talk about reduction. So we've got just one major reduction reaction to talk about. We've got a whole slew of oxidations, it turns out. So we'll start with reduction first. And just like we covered back in the ketone and aldehyde chapter, you can reduce a ketone or aldehyde with either LiAlH4 or NABH4. Well, LiAlH4 is super strong. It's a super strong base as well, and it doesn't really handle being under protic conditions. With all these alcohols, it would be a poor choice here, and we don't use it. But sodium borohydride, a little milder reagent, perfect choice. So it's not going to be so reactive as a base that it's going to deprotonate any of these hydroxy groups, so we don't have to worry about it like we would with LiAlH4, but it'll still reduce both ketones and aldehydes. And so in this case, if we reduce the aldehyde here to an alcohol, so we call this an alditol. So in this case, typically it's D-glucotol, but it's an alditol. So you might commonly hear these referred to as sugar alcohols. Sometimes we use them as sugar substitutes because your body doesn't metabolize them in the same way as a sugar does, and so you don't get the calories you normally would from an actual sugar. So, and that's sodium borohydride pulling this off, and we see one little nuance here for a ketose. So with the ketose, if you reduce the ketone, so you're going to form a chiral center. We didn't have that problem with the aldehyde. With the aldose, we actually were reducing the aldehyde to an alcohol, and it was just a CH2OH group that it became on the terminus, and it wasn't a chiral center. But with the ketose, it's going to turn into a chiral center. And we don't have any stereospecificity with sodium borohydride, so depending on which face we attack, the front face or the back face, you're going to get two different stereoisomers, in this case a pair of epimers, and so you could get D-glucotol still, but you might also end up with D-mannitol instead. And there's not really a great way here to make sure you only get one versus the other. You're going to get that pair of stereoisomers with sodium borohydride. So I'm taking a look at a slew of oxidations. We'll start with the mildest of them and kind of work our way to more stringent oxidations. And we're going to start with aqueous bromine, so Br2 in water. So we're going to buffer it at pH 6. Now, a lot of textbooks won't write it with that buffer pH 6, but it is important to the reaction conditions. But whether you see it written with it or not, you should treat it the same. And so the idea is that at pH 6, we're under mildly acidic conditions. And the reason that's important is the epimerizations and isomerizations that were possible under basic conditions are not going to be possible here. So that'll have one important repercussion, as we'll see in a little bit. But buffered under mildly acidic conditions. And in this case, we're going to oxidize an aldehyde to a carboxylic acid. So you might recall back in the alcohol chapter, we learned that you could have probably carried this off with chromic acid or potassium permanganate or something like that as well. But in this case, that wouldn't be appropriate because you might get some other reactions with some of the other things here, and we want to just selectively oxidize the aldehyde to the carboxylic acid. Chromic acid would have also reacted with, say, the primary alcohol and maybe the secondary alcohols, and you would have got a whole slew of mixture of products. But here, this is selective just for oxidizing the aldehyde to a carboxylic acid, of our aldose here. So the result we call an aldonic acid, and typically from glucose, we get D-gluconic acid. When we go to try this reaction with a ketose instead, we get no reaction. And this is important. And again, the reason this is carried out under acidic conditions, if it was carried out under basic conditions, well, then you'd have an isomerization taking place between the ketose and the corresponding aldose. And a little bit of aldose could actually react with Br2 in water to get oxidized. And once it did, then some more ketose would equilibrate, forming more aldose, which would then get oxidized. And pretty soon, all of it would get carried through and get oxidized. But because this is done under mildly acidic conditions, that isomerization is kept at bay. It does not happen. And so ketoses are not going to react here with bromine and water. Now the next oxidation we'll take a look at is with the Tollen's reagent or the Benedict's reagent. So these two reagents are somewhat synonymous. They accomplish exactly the same reaction as we'll see, and they're both considered mild oxidizing agents, therefore again selectively oxidizing aldehyde to the carboxylic acids, as we'll see, with one little twist that we didn't get with the Br2 in water, as we'll see. Tollen's reagent is an ammoniacal solution of silver ions, so silver ions mixed with ammonia. It is a basic solution when you've got ammonia there. And then Benedict's reagent is a cupric solution of sodium citrate, and there's also sodium carbonate in there, which is also going to make it a basic solution. The fact that these are both basic solutions means isomerizations are now possible with aldoses and ketoses, and that'll be important when we start talking about considering these reactions for a ketose. Now, one thing you should note here for these two reagents, both give a kind of a characteristic test. We often use these as a test for testing to see if we have aldoses and ketoses, and it turns out that both aldoses and ketoses are going to give a positive test. So with the Tollen's reagent, when this corresponding oxidation, you're going to oxidize an aldehyde to a carboxylic acid, just like we did with bromine and water here. And when that oxidation happens, it turns out the silver ions are going to get reduced to metallic silver. If you carry it out in a test tube, you're going to have that metallic silver form a mirror-like coating around the outside of that test tube, I guess the inside of the test tube technically, and it gives kind of a mirror sheen to it. It's really kind of a cool demo, but real characteristic positive test. Benedict's reagent, on the other hand, you're going to actually precipitate out some copper oxide, which is kind of a red-brown precipitate. And so if you get that red-brown precipitate, that's your positive test for Benedict's. But either one of these gives a positive test for either an aldose or a ketose, as we'll see. And we call sugars that actually react with these oxidizing agents, well, they are therefore acting as the reducing agents, and we call them reducing sugars, and that's going to mean something here. So a positive Tollen's test or a positive Benedict's reagent means you've got a reducing sugar, assuming you had a sugar. So now let's consider the difference with a ketose. And again, with bromine and water, isomerization was off the table because it was carried out under mildly acidic conditions. But again, whether you've got the Tollen's reagent or the Benedict's reagent, they're both under basic conditions. And so if you've got a ketose, it's going to isomerize to some small extent, and you'll have a little bit of aldose present as well. And it's the aldose that can get oxidized to a carboxylic acid. And if it does, well then this equilibrium is going to shift to make a little more aldose, which can again react with Tollen's or Benedict's reagent to make a little more carboxylic acid. And eventually all of your ketose will get dragged through the equilibrium here according to Le Chatelier's principle, and eventually all get converted into an aldonic acid. And that's why ketoses, even though in principle ketones are not oxidizable, well, if they can isomerize to the corresponding aldehyde, then they would eventually all get oxidized to aldonic acid. And so that's why both ketoses and aldoses give positive Tollen's and Benedict's tests. That's why both ketoses and aldoses as monosaccharides are going to be reducing sugars. So then the question comes up, well, when do you not have a reducing sugar? So, well, you've got a non-reducing sugar if you've got a glycoside. So, and we talked about those a little bit earlier in glycoside formation. So typically these are only going to form when you've got the cyclized version of the sugar. So, but even if you got a cyclic version of a sugar in solution, it's going to be in equilibrium with some small amount of the open chain form as long as it's not a glycoside. So, but if your anomeric carbon here, so if that what's normally a hemiacetal, if it's converted into an acetal, as the case is here, and again, you know it's an acetal if your anomeric carbon, which again is bonded to two oxygens, and if neither one of those oxygens is an OH, a hydroxy group, they're both ORs, they're both oxygens bonded to additional carbon chains, that's when you know you've got an acetal. So, and it's acetals that are non-reactive, even under basic conditions. So if they're non-reactive, they're not going to get oxidized by the Tollen's reagent or the Benedict's reagent, and so they are non-reducing sugars. I'll give you another example here. So we're going to learn about disaccharides in the next lesson. So, but it's instructive to kind of pull this up. So if we identify where the anomeric carbons are for both of these monosaccharides that are joined together in this disaccharide, be instructive. So, and again, it's always going to be one of the adjacent carbons to the oxygen in the ring. That's going to be the anomeric carbon. So if we look on this side, well, this carbon's not bonded to any additional oxygen atoms, so it's not the anomeric carbon, but this one is. In addition to being bonded to the oxygen in the ring, it's bonded to this oxygen right here. That's your anomeric carbon. And neither one of these oxygens is a hydroxy group. They're both oxygens bonded to additional carbon chains. That is an acetal. And so from the perspective of the monosaccharide on the left, so his anomeric carbon's part of an acetal, part of a glycoside in this case. Now, if we look at the one on the right here, find his anomeric carbon. Well, again, it's got to be one of the ones bonded to the oxygen in the ring. Well, this one on the right is not bonded to any additional oxygen atoms, but this one on the left is. It's bonded, again, to this oxygen, joining the two monosaccharides together. And again, neither one of those oxygens is a hydroxyl group. This is not a hemiacetal from his perspective either. It is also an acetal from his perspective. So, and in this case then, we don't have a hemiacetal anywhere in our structure, only acetals. And once again, that's what's going to make this a non-reducing sugar. It will not react with either Tollen's or Benedict's reagents. So I don't want you to come away with, well, anything that's got the cyclic form of a sugar is going to be non-reducing. That's not true. So the key is it an acetal or hemiacetal? If there's any hemiacetals present anywhere, so it is going to be a reducing sugar. So if you take a look at this first one here, and you got the cyclic form of alpha glucose here, and there's your anomeric carbon, again bonded to two oxygens, and one of them is a hydroxyl group. This is a hemiacetal. So, and as such, so it will be in equilibrium with its open chain form, which is an aldehyde, and that aldehyde can indeed get oxidized to a carboxylic acid. So, and this is indeed a reducing sugar as a result. So if we take a look at the disaccharide here, so we've got our anomeric carbon for the monosaccharide on the left right here. That's the carbon bonded to two oxygens. Neither one is an OH. And so that is an acetal, and that acetal relative to this monosaccharide over here is not going to be reacting with either Benedict's or Tollen's reagent. So however, if we look on the other side here, so there's our oxygen in the ring. One of the two adjacent carbons is going to be the anomeric carbon, and it's this guy right here. That's your anomeric carbon. And in this case, he is bonded to two oxygens, and one of them is an OH, and that is a hemiacetal. So in being a hemiacetal, this one would be in equilibrium with its corresponding open chain aldehyde form, aldose form, and would react with Benedict's reagent or Tollen's reagent. So in this case, when you've got a disaccharide, all you got to do is find one hemiacetal. If you've got a polysaccharide, all you got to do is find one hemiacetal, and that hemiacetal could indeed get oxidized to a carboxylic acid with the open chain form it's in equilibrium with. So it doesn't matter if all of them except for one are all acetals. As long as you got one hemiacetal, this is now going to be classed overall as a reducing sugar. Now we've got one more oxidation to take a look at. That's with a stronger oxidizing agent than any we've looked at before, and that's with nitric acid in this case. So we're going to get a similar reaction, but with one additional reaction that's possible. So we're still going to oxidize aldehydes to carboxylic acids. But additionally, we're also going to oxidize primary alcohols to carboxylic acids as well. So the secondary alcohols in the interior of our aldose here, they're not going to get touched. Secondary alcohols are not going to get oxidized by nitric acid. But your aldehyde to a carboxylic acid, but also the primary alcohol at the other end, also to a carboxylic acid. And so you're going to end up with what used to be a sugar now being a carboxylic acid at both ends, and we call that an aldaric acid. Specifically, this is glucaric acid. But that's an aldaric acid. And one thing to note, this is happening under acidic conditions. And if we had a ketose, and we normally wouldn't even talk about this with ketoses, because under acidic conditions, it's not going to be in equilibrium with the aldehyde. And ketones don't get oxidized to carboxylic acids. They don't typically get oxidized by normal means anyways. They're definitely not going to get oxidized with our nitric acid in this case. And so we normally wouldn't even talk about it. Now, you'd still have primary alcohols that could get oxidized to carboxylic acids, but the ketone would stay a ketone. And it's normally not going to get brought up in this context with monosaccharides. All right, we're going to finish this lesson off with a couple reactions that were kind of important in early carbohydrate chemistry here. And one of them is going to lengthen the length of an aldose by one carbon, and one's going to reduce it by one carbon. And both of them got their place. Now, in lengthening it with one carbon, we call it the Kiliani-Fischer synthesis. You've got to start with an aldose, and that aldose is going to get longer by one carbon. So here we've got an aldopentose with 5 carbons. And we're going to end up with an aldohexose with 6 carbons. So reagent you start off with is HCN, hydrocyanic acid here. And we learned that with an aldehyde and HCN back in the chapter on ketones and aldehydes that you're going to form cyanohydrin. So and what happens is this oxygen is going to get protonated. So in this oxygen right here becomes this hydroxyl group here, either one of those. So and then cyanide's going to come and attack, so kicking these electrons out, leading you to one of these structures. So and we call these cyanohydrins. So we definitely learned about cyanohydrin formation back in the ketone aldehyde chapter, so nothing new here. Now, we're going to reduce these cyanohydrins using hydrogen and a poison catalyst. This might look like Lindlar's catalyst. But we're going to do it under aqueous conditions, which is going to have one key effect here. So what's going to happen is this carbon-nitrogen triple bond is going to get reduced to a carbon-nitrogen double bond. And that carbon-nitrogen double bond is going to look a whole lot like an imine. I want to review something we learned about with imine formation. So with imine formation, we looked at this a couple of different ways. So we started off with a ketone or aldehyde. We reacted it with a primary amine under acidic conditions. And that carbon-oxygen bond was replaced with a carbon-nitrogen double bond. And it loses the 2 hydrogens along the way, so we lose water. And this carbon-nitrogen bond with our group, this is now your imine. But what we learned is that this reaction was completely reversible. And we could reverse the reaction if we just added aqueous acid, so essentially H3O+, and convert it right back into a ketone. Well, we're doing this the other way around. So we're going to form this imine right here. Because we're doing it under aqueous conditions, that imine is going to get converted into a carbonyl group, and not a ketone in this case, but into an aldehyde, and that's the magic behind this reaction. Now, this cyanohydrin formation, so when we have the cyanide group attacking this sp2 carbon right here, there's no stereospecificity. We're going to form a new chiral center right here, which is going to become carbon 2 in our aldohexose at the end. So in forming that new chiral center, since there's no stereospecificity, you're going to form a pair of epimers in the process. No way around it here in this Kiliani-Fischer synthesis. But overall, one additional carbon, in our case going from an aldopentose to an aldohexose, but you could go from like an aldotetrose to an aldopentose. So the idea is you're just adding one additional carbon to an aldose. And finally, the last reaction we're going to take a look at is the Wohl degradation. So in the Wohl degradation, instead of lengthening the chain by 1 carbon like we did in the Kiliani-Fischer synthesis, it's going to reduce the length of an aldose by 1 carbon instead. And it's almost exactly the reverse process that we learned for the Kiliani-Fischer synthesis. All right, so the first step is reaction of an aldose with hydroxylamine. So in hydroxylamine, you might recall, so when we talked about imine formation here just a second ago, it would react a primary amine with an aldehyde or ketone, and you turn your carbon-oxygen bond into a carbon-nitrogen bond. Well, it turns out if your R here happens to be a hydroxyl group, then we wouldn't call this an imine. So although mechanistically it would form the same way, we call it an oxime instead. And so the first intermediate you form here is going to be an oxime. Then we add acetic anhydride, and that's going to oxidize your oxime to a nitrile instead. You might recall that was one of the intermediates when we went the other way in lengthening the chain. Well, now it's going to be an intermediate when we're shortening the chain as well. And then finally, we're going to add a strong base, and in this case, sodium methoxide is going to be our base of choice. And so let's say we draw this hydrogen out right here to make this a little easier to see. We'll draw it out. So, and then we're going to take our base here, and use it to deprotonate. That's going to free up these electrons to come and form a double bond, a carbon-oxygen bond, and kick off the cyanide as a leaving group. And so this carbon right here is our new carbonyl carbon right here. And notice we don't have the same problem we did with the Kiliani-Fischer synthesis where we formed a new chiral center. So we have actually the opposite where we lost a chiral center. So we don't have to worry about forming multiple isomers or anything like this. We actually lost a chiral center, not formed one, and we just form an aldose with 1 fewer carbons than the original aldose we started with. So in our case, we went from an aldohexose down to an aldopentose. And that's going to conclude this lesson. And if you found it helpful, then help me out with that YouTube algorithm, and a like and a comment, pretty much the best things you can do to help me with that. If you are looking for the study guide that goes with this lesson, if you are looking for practical materials for your organic chemistry course, then you might take a look at my organic chemistry master course. I'll be sure to leave a link in the description below. And if you're studying for finals, part of that master course is also some final exam rapid reviews, where I review rapidly all of OChem 1 in a little less than 6 hours, and all of OChem 2 in a little less than 6 hours, and include practice final exams as well. If you're studying for the ACS standardized final exam, I've also got a refresher course for that. I'll be sure to leave a link in the description for that one as well. In the meantime, best of luck on your finals. Happy studying.